Welcome. My name is Rudolf Weeber and I'm a researcher at the Institute for Computational Physics at the University of Stuttgart. In this talk I would like to show you some tools to manage your simulation data. Why should we care about managing simulation data? Well, if we do it well, then we have quick access to it and can make good use of it easily. And also, if we do it well, we or another person in a few years can still access the data and understand how it was generated and reproduce it and pick up the project where we left it. The goals would be making your simulation data easily accessible and explorable, and then clearly link the results of your simulations to the parameters that you used to generate them. That includes the software version you used, and also make it easy to reproduce and extend your project at a later stage. So what will I be showing you? First, we are going to look at Git, which is a source code management tool which lets you track the different versions of your simulation script over time. So for instance, you can note down the version that you had when you ran the simulations and later go back to that particular version of the simulation script if you want to reproduce them or add more data. You can also see what changed over time. Then, passing the parameters to your simulations, we are going to look at the argparse module for Python. And this is very handy because you can also store the parameters that you pass into your simulation script. Then we are discussing storage of simulation data, and here mainly structured formats. So instead of just putting everything in a text file where you have to remember what column is what variable, better use a structured format, and Pickle is one Python module that lets you store structured data. And last but not least, we are looking at Pandas, which is a data analysis library for Python, which is extremely popular in the data science community, and we are going to use that to aggregate and sort and filter our simulation results. Let's begin with tracking your simulation script. So the aim is that you can always figure out what version of a simulation script you used for a simulation, and that you can track your changes over time, and that you can also go back if you change your mind or switch between different versions. That's what Git is excellent for. Git is the de facto standard for source code management, so it's used for everything from the Linux kernel to the source code of Microsoft Windows, and also many open source projects, including ESPResSo, is managed using Git. So it tracks the change of your source files over time, and also it tracks different versions if you have them. It also tracks who makes what changes, so that you can ask the person. So it's well suited for collaboration in general. It supports very large teams. Although it doesn't require a central server, which is very handy because you can use its full capabilities on your laptop when you are on the go. Still, collaboration is important, and then you need a place to share your data, and that is what platforms like github.com or gitlab.com are for. So, for instance, we use github.com to host the ESPResSo source code and to keep track of the changes that are made, and to keep track of the changes that people want to make and to discuss them in public. When working with Git, you have to be aware of a few terms. The most important one is the repository. And that's the place where your files and their history and the metadata is stored. That is not only the content, but also who changed them, how and when, and also different versions you have. On your computer locally, that's typically a folder, but you can connect to remote repositories to exchange code with other people. Then there is the commit. Commit is the specific state of your files and their history. And you can reference those commits by citing their so-called commit hash. So that's a long string, and the first few characters typically are unique, so you can just refer to a commit and go back to that commit, or tell another person, hey, please explain what you did in that specific commit. Also, with each commit, metadata like authorship and date are stored. And lastly, there are branches. So branches are used to take care of different versions of your code. So for instance, if you develop a new feature, you do that in a different branch. So you can switch between the branch where you are trying out the new feature and your standard branch where the well tried out version of your code is, which you use for production simulations. Git is a command line tool, although modern IDEs such as Visual Studio Code offer a graphical interface as well. Here are the 5 most important Git commands you need to know. Git init, that's where it all starts. It takes a folder and converts it into a Git repository. Git diff is used to show changes, both with respect to the last commit and also to compare different commits. Then git add you use to tell Git which of the new files or which of the changed files you wish to include into the next commit. With git commit, you create the actual commit and provide a commit message which explains what changed in this commit. And last but not least, git log lets you see how your stuff changed over time. So it basically shows the history of commits. So we start in an empty folder for our project, which I've already created. And the first step is to use git init to convert it into a Git repository. If we list it again now, you can see that a new directory has appeared, which is called .git. That's where the repository information is stored. You should leave that directory alone. Git takes care of it, and you can use the remaining folder for your simulation project. Okay, let's create our simulation script. And the content doesn't matter for this demonstration, I just leave it blank. Then we use git add to tell Git that we want to add this to our repository. Done. There is git status, which lets you show the status of affairs. That tells you that we have now a file which is staged for the next commit. And now we can commit. Once we do that, an editor opens and asks us for the commit message. Here we write initial commit, for instance. So we have created our first commit. We use git log to see it. Okay, let's make changes. We open the simulation script again and put in a hello world message. Done. Save. We use git diff, which tells us what is changed since we last committed. And we use again git add to stage this change for the next commit. So you can add more files in a single commit. And good practice is to put stuff together in a commit that actually belongs together in terms of its content. Git commit. Now we have to add a commit message. We say that we added this functionality to our simulation script and save. We use git log again. And as you can see, now we have 2 commits. As you can also see, date and author information is stored together with the commit. There's also the commit hash, which we can use if we want to refer to a commit. For instance, we can use git diff to do comparisons. So git diff to E9E, the first few digits will do, and so we can see the difference between the initial commit and what we have currently. And that's the use of the most basic commands. Of course, there are many more, and it's worth your time learning them. The remaining tools discussed in this talk I'll show using an example scenario. We're going to look at the Lennard-Jones fluid, which we are simulating at different temperatures and densities. We're going to measure the pressure and pair correlation functions, and for each pair of temperature and density we're going to run several simulations with different random numbers, so we can do averaging afterwards. This is called trivial parallelization and leads to less noisy results. Our project consists of 3 files. First of all, there is the lennartjones.py, which is the actual simulation script which will run a single Lennart-Jones simulation. Then there is a gatherresults.py script which takes a list of folders which contain results from the individual simulations and gathers them into a central file which we later use for analysis. So we have all our data in one place now, independently of where we ran our individual simulations. And then lastly, as an example on how to access your simulation data efficiently, there is displayResults.py. And we'll go over these files one by one now. First, we need to get the simulation parameters into our simulation script. And one of the easiest and safest way to do that is via command line arguments using the argparse module. So that's what I would like to show you now. Argparse is a module where you register all your command line arguments, and then it does all the handling of the command line arguments and just gives you back an object where the resulting parameters are stored in. This object you can also later simply store together with your simulation data. In this way you always store the parameters you use to run your simulation, in our case for instance the density and the temperature, together with the simulation results such as the observed pressure for that parameter set. Okay, let's see it in practice. So you use argument parser in 5 easy steps. The first one is to import the Python module. The second one is to instance the parser object. So you create a variable which will hold all the command line arguments and which you can use to interact with the parser. Then you register all the command line arguments. As an example here, we register an argument for the volume fraction of type float. So we expect a floating point number from the user, and then we call the parseArgs method of the parser to process the command line arguments and store the output in a variable. And this variable we can then in the 5th step use to access the command line arguments in our script. So for instance here we print the content of the argument volume fraction. Let's see how that looks in the simulation script. So let's go to our simulation script, lennartjones.py. The script is basically a Lennart-Jones fluid as you know it from the Lennart-Jones tutorial. If you haven't done that yet, I would refer you to ESPResSo's Lennart-Jones tutorial to get familiar with the simulation itself. But let's talk about how we get in the command line arguments. First, here we import the argparse module. Then together with the other Python modules used in this script. Here we instance the arguments parser in a variable called parser. Now we register all the arguments. First we have a simple floating point argument for the volume fraction. It is required, so if the user doesn't provide it when running the simulation script, they get an error message. Then there is kt. Here you can see how we can provide a help message which will be displayed in the command line help of the script that the user sees, for instance, when they run it with -- help or run it with wrong command line arguments. Here you see how to handle an optional argument that can be either provided or not. And if it's provided, then we store true in this argument. So this purely repulsive switches between 2 types of the Lennart-Jones interaction in our simulation script. So what you have to note here is the action equals store true field. Then we have the seed for the random number generator, which is of type integer. And now we provide the default value equals 1. So if the user doesn't provide this argument when running the script, one will be used instead. Last but not least, a string type argument for the output file. Once we have registered all our arguments, we run the argument parser in this command. The result will now be in the variable args, and now we can just use the individual arguments by their name. For instance, in these 2 lines of code, we validate that the volume fraction that the user has provided makes sense. Let's see it in action. So first of all, I run the pure script with no arguments. That gives me an error message which explains what I did wrong, i.e. I didn't provide the required arguments. I can run our simulation script with --help. Then I get the command line help, auto-generated by argparse. This uses the help message that I have provided when defining the arguments in the previous steps. Okay, and now if I actually provide the arguments, I can run a simulation. So we have to provide a volume fraction, 0.1, a kt, let's say 1. Let's use the purely repulsive Lennard-Jones potential, set the seed of the random number generator and the output file. Of course, you might argue that typing these argument names is more work. On the other hand, it cannot happen to you this way, that you swap by accident the order of command line arguments. So it's much safer, and the time that you spend typing you get back 10 times by avoiding unfortunate errors. We've provided all arguments, now we can run the simulation. Let's say you have your simulation script up and running. The next question would be how to store your data safely. The classical way that people typically learn first in programming lessons is text files. However, that's not actually a very good choice. The reason is they are unstructured or mostly unstructured, so it's very easy to introduce mistakes. For instance, in a text file, the column header and the data type are not directly strictly linked to the content of the column. So it can easily happen that you by accident mistake the order and use a different column order in your simulation script and in your analysis script, and mistake 2 columns, and then you get very difficult to debug mistakes in your results. Better use a structured format which maintains the knowledge about what a specific data is and how it was generated and what its type is. One relatively easy way to do some of that is the Pickle module in Python. So the Pickle module can store most Python objects in a file and later load it back again. And we'll be using this for both storing the command line arguments that you pass to your simulation and for the actual simulation data. Although I'm showing you Pickle in action now in the simulation script, let me also mention some alternatives that people use. First, the Numpy library has its own data format, so it can store arrays including shapes and data types. People use that in particular if they have to store huge arrays, which works very well. So even hundreds of megabyte sized arrays can be stored this way. Then there's the Pandas library, which is a data analysis library for Python, which we'll take a look at later. It can read and write all kinds of structured formats. Then there is YAML, which stands for Yet Another Markup Language, which is a text-based structured format which people use often for configuration files, but you can also use it to store or load simulation parameters. It's text-based, so that can be read by machines and by humans. For very large projects, people sometimes also use databases to store their simulation data. especially if the parameter space or the dataset is huge. That requires a bit more work, and I'll not cover that here. Using Pickle is really simple because you only need to know 3 commands. You need to import the module, and there's pickle.dump, which saves an object into a file, and there is pickle.load, which loads it back. So let's see it. Import Pickle. Done. Okay, now Pickle can store most Python objects. As a demo, I now create a list which contains a number and a string. Let's see it. Good. So the first command, pickle dump. What we want to save, the list we've just created, and now we need a file handle. The quickest way is to open it just in place. File name and the file mode, it should be write binary, so WB. Done. Here's our Pickle file. Okay, let's load it again. So pickle.load. Again, we have to pass a file handle, which we can just create in place. Again, the file name and the file mode, which should now be read binary. Done. Let's look. And now M contains what we just loaded from the file. That's all there is to it. Now in the simulations, the best thing to store would probably be a dictionary, which uses key value pairs, so you can label all the stuff you put in, rather than just having a list where you have to remember which element is which. Here we are right before the main integration loop where we calculate our data. First, we create a Numpy array, which will contain all the pressures that we record during the simulation. Then we create an array which stores a single radial distribution function. We define an observable which calculates the radial distribution function in ESPResSo. You also learn about this in the Leonard Jones tutorial in more detail. Then comes the main integration loop, which starts here. We propagate our system by a few time steps, and then we take measurements. So we record the current pressure. In some greater steps, we also collect a radial distribution function. Then, once the simulation has finished, we have to store the results. To do that, we create a Python dictionary which contains key value pairs for our simulation results that we want to store, and for the input parameters. That's the first one, args. So here we store the output that we gained at the beginning of the script using the argparse module. In this way, together with the simulation data, we have the input parameters that were used to run the simulation. Then we save the arrays containing all the pressures, and we save the average radial distribution function. Then we save the bin centers of the bins of the radial distribution functions, and that's it. Now all our stuff we want to store is in one simple variable, and that we can now pass to pickle dump. Here we open the file, and here we save. As simple as that. I recommend to use that in all simulations if it's possible, and you can go to bigger solutions if you need to. I've now run the simulations for different temperatures and densities, and also for different random number seeds, so I can do some averaging. So let's come to Pandas, which we'll be using to aggregate and analyze our simulation data. Pandas is a data analysis library for Python, which is really popular in the data science community. I would also say it's the de facto standard there. It's built around the data frame class, which is kind of a NumPy array on steroids. So it offers some additional benefits. For instance, the data columns have names. You can filter very easily by arbitrary criteria, and you can do aggregations such as sums and averages and minima and maxima. Pandas can also cope very well with missing data, for instance. So that's what we'll be using. Our first task will be to collect the output from our individual simulations, which we may even have run on different systems like compute clusters, and put them all together in one big data frame where the results are summarized. And that we can then use for analysis. Please recall that each individual simulation created a Pickle file which contained the simulation parameters and the simulation results for that simulation. Now our task is to collect the data from these individual files and aggregate them into a Pandas data frame, which we then can use to quickly get an overview of our data. So let's look at the Python script which does the job. It's called gather results. It needs a few modules. First of all, of course, Pickle, because that's how we save and load our stuff. Then Pandas, because we are collecting our data into a Pandas data frame. And then the argparse module, because that's how we process command line arguments always. Okay, let's look at those command line arguments. First, there is an output file, which is where the Pandas data frame containing all our data will be stored. And then there are many input files from the individual simulations. So note the narg equals plus here for one or more argument. Good. First of all, we create an empty list. That's where the individual simulation results will go. Then we have a loop over all the file names which have been passed in via argparse. For each of those files, we load the data using Pickle. Now comes the important part. We append to our list a dictionary with key value pairs, and now each key here corresponds to a column name in our data frame, and then the value corresponds to one row in that data frame. So you can see that we use one column for each simulation input parameter and one column for the pressure and a column for the radial distribution function and for the radial distribution function bin centers. So once this loop has completed, we have created a list of dictionaries, and now we can simply cast this into a Pandas data frame with this single command. The only task which is now left to this script is to save this data frame using Pickle. And Pandas and Pickle are linked, so you can see you can save the data frame with a single command to a Pickle file. And that's all there is. Now we have one file which contains all the simulation parameters for which we have conducted simulations and the corresponding results. So let's run our collection script. Gather results.py. We specify the output file where all the data will go. PKL is the default extension for Pickle files by convention. And then we specify the files for our individual simulation. I'm using wildcards here. Let's run it. Done. We have collected results from 120 simulations. After we have gathered our data into a single file, we can now take a look at it. I've written a Python script to demonstrate the three most important tasks here. The first is filtering. Let's say we want to see only results for kt equals to 1 and those where we use the purely repulsive Lennard-Jones interaction. Then there is sorting. Let's say we want to sort by volume fraction, and then there is averaging. So let's say we average over the simulations with the same input parameters but with different random seeds. The Python script in action looks like this. It's called display results.py. It takes as input the file name where our results are gathered, and the filter criteria such as kt equals to 1 and the purely repulsive flag being set to true. Then we sort by volume fraction and by seed. Here are our results. Okay, we also want to average over different seeds. So let's specify that. Done. Of course, this script displays the results, but instead you could just as well write using pyplot a plotting. So let's examine the code of the display results script. First of all, there is command line argument processing, as you have seen it now several times using argparse. Then we load the data using Pickle, and the result will be again a Pandas data frame. Let's go to the first task, which is filtering. Here we write a function which filters an arbitrary column by an arbitrary value. So it takes the column name, the value to filter by, and then the data to be filtered in the form of a data frame. First we see if the value is even set, because if it isn't, we don't filter. Those are these two lines. Next, we do the actual filtering, which is extremely simple in Pandas, because as an index to a data frame or as an argument to the angular braces, you can just specify the filter criterion as it's done here. So you write into parentheses that the content of that column equals, with 2 equals the value, and put that into the angular braces. That's all there is. You return it, and the result is a filtered data frame. Okay, now we execute the filter for the columns for which we support it. That is the temperature, the volume fraction, and the purely repulsive flag. These are those 3 lines. Now comes sorting. If we have even specified a sort criterion, then let's do that. And there's also a simple function for a data frame which does the sorting, which just looks like this. Totally simple. The only thing which remains is the averaging, which starts here. So if on the command line we have asked for averaging, we use a so-called group by operation. Now first we have to say which columns have to agree for simulations to be averaged. So we only want to do an average for simulations which have the same KT, the same volume fraction, and the same content of the purely repulsive flag. That's the group by columns. Okay, and then we execute the group by and replace the data frame by the result. So we specify the group by columns as index equals false is what you need to get back a single data frame with a single index. And then you have to specify the name of the result column, which will be average pressure, and the mean function. That's it. If we don't group by, then we somewhat limit the columns that we want to see in the output. This is done here. So we create a list with the names of the columns we want to display and only keep those columns in the data frame. And then we can just use print to show the result. Of course, instead of the print, you could put a plot command here to plot your results. So in summary, I've showed you some tools to manage your simulation data and demonstrated them using a Lennard-Jones demonstration scenario. I'll publish the scripts so you can use them as a basis for your own projects. The individual tools that you have seen were Git, which we use to track the changes to our simulation script. Then we used argparse to do all the command line argument parsing in Python. And recall that it's handy because you can also directly use Pickle to store both your simulation results and the arguments that have been processed using argparse. And last but not least, we used Pandas to gather our simulation data into a single data frame, which we then used for filtering, sorting, and averaging. So investing in those tools is very good for the reproducibility of your simulations, because you have your data in a structured format, and because you get some linkage between the input parameters and the simulation results. So hopefully the error rate in simulation workflows goes down. I think it's well worth the effort to learn those tools. Of course, all of these tools can do much more than I've shown in this little talk.